Hi everyone, welcome to the course Low Power VLSI Design. In this course, we are going to see one of the most important aspects of modern VLSI. VLSI stands for Very Large Scale Integrated Circuit, which plays a major role in the semiconductor industry, and that is one of the main factor in the semiconductor industry is power consumption. So today's electronic devices such as smartphones, laptops, all the wearable devices like wristwatch what we are having in our hand, and IoT systems that are embedded with other applications that demand high performance while consuming very little power, which is becoming a challenging task day by day. Throughout this module, we will understand why power dissipation occurs in CMOS circuit, how it affects the performance of the system, and technique that are used to reduce the power consumption with improved efficiency. Let us first look at the syllabus covered in this lecture series. The first part focuses mainly on power dissipation in CMOS circuits. We will study various sources of power dissipation, including dynamic power, short circuit power, and leakage power. Then we will understand the structure and operation of MOSFETs, beginning with the MIS structure, followed by long channel and submicron MOSFET, which are the recent technology that is prevailing now. We will also discuss important leakage mechanisms such as gate induced drain leakage, or shortly called as GIDL. After that, we will learn about load capacitance, principles of low power design, and the practical limitations at both the device and circuit level. The second part of the module focuses on power estimation. Here we will learn as an engineer how to estimate power consumption before fabrication using concepts such as signal modeling, signal probability, switching activity, binary decision diagrams, short form we can call it as BDD, and average power estimation in combinational and sequential circuit. At last, we will be able to analyze where power is consumed in CMOS circuit and apply various techniques to reduce it. So this is the first thing, power dissipation in CMOS circuit. This lecture mainly focuses on power dissipation in CMOS circuits. So CMOS stands for complementary metal oxide semiconductor field effect transistor. CMOS technology is widely used in almost every digital integrated circuit because of its low power consumption and high noise immunity, which is the advantage of mass circuits over BJT, that is bipolar junction transistors. Although CMOS is considered as energy efficient when compared with other transistors, it still consumes power during operation. As transistor size continue to shrink into nanometer technology, power dissipation, that is heat dissipation, has become one of the biggest challenges in VLSI design. In this series lecture, we will understand what are the various reasons behind this power consumption and explore the techniques to minimize the power consumption. Now let us understand the three major sources of power dissipation. The first source of power dissipation in CMOS circuit is dynamic power dissipation. Dynamic power is consumed when the output of a CMOS circuit changes from logic 0 to logic 1 or vice versa, that is from logic 1 to logic 0. During the switching process, the load capacitance connected to the output charges and discharges. So whatever circuit we have, it will be connected with voltage source, that is VDD, and ground. Whenever there is a change in the input from 1 to 0 or 0 to 1, the load capacitance will be charging and discharging. Since switching occurs continuously in digital circuit, this becomes the dominant sources of power during active operation. This is what the main reason of dynamic power dissipation. And the second case is nothing but short circuit power dissipation. Whenever the input changes, there is very short period timing during which both PMOS and NMOS transistors conduct simultaneously. This creates a temporary direct path that exists between power supply to ground, resulting in a short circuit and power loss. The third source is nothing but leakage power dissipation, which cannot be completely eliminated, but all these three power sources should be minimized. Even when a transistor is turned off, very small leakage current continue to flow due to various physical mechanisms. That is what we are going to see in the upcoming topics, such as subthreshold leakage, gate leakage, and gate induced drain leakage, commonly called as GIDL. As technology scale is below 100 nanometer, leakage power becomes increasingly important. That is when size is getting shrink. So whatever electronic devices we are having, the size of the device plays a major role. So when the size is getting reduced, leakage power becomes a major factor which is to be concentrated. In upcoming lectures, we will study each of these power components in detail. Next, why is power important in VLSI? Now let us discuss why reducing power consumption is important. Then we will go with how to minimize the power dissipation. Modern electronic systems are expected to be faster, smaller and more energy efficient. If a circuit consumes excessive power, several problems arise. The first problem is heat generation. So whenever heat generation occurs, there is a chance of thermal runaway, which means damage of the own device because of its heat dissipated by the device, and electrical energy that is not effectively converted into heat. This excessive heat can damage electronic components and reduce their lifetime. And the second problem is reduced battery life. Portable devices such as smartphones, laptops and smartwatches and wireless sensors depends on batteries. Low power consumption directly translates into longer operating time. Third one is lower system reliability. High temperature accelerate device aging and increases the chances of failure, which leads to reliability of the system factor. Finally, high power consumption increases the cost of cooling systems in the data center. Whenever heat increases, we want to minimize that heat by having extra cooling system and high performance computing application. Therefore, today's VLSI design has focused not only on speed and area but also on minimizing power consumption. Now let us focus on how power estimation is to be done to focus the power dissipation minimization concept. Before manufacturing an integrated circuit, engineers need to estimate how much power it will consume. This process is called as power estimation. Estimating power during the design stage helps identify high power blocks early and optimize the design before fabrication, and this process is called as signal modeling. Signal modeling represents digital signals mathematically so that their switching behavior can be analyzed. Second concept is nothing but signal probability. Signal probability represents the likelihood of a digital signal being at logic 1 or at logic 0. This information helps estimate the switching activity, which is a continuation of signal probability. Switching activity is whenever a signal changes from 0 to 1 and 1 to 0, it consumes dynamic power. Therefore, circuits with more frequent switching generally consume more power. Finally, engineers estimate the average power consumed by combinational circuit and sequential circuit using various analytical methods, including binary decision diagram or BDD, and these techniques helps designer build circuit that meet performance requirements while minimizing energy consumption. To summarize today's lecture series, we introduced the concept of power dissipation in CMOS circuit and discussed why low power design has become a critical requirement in modern VLSI design. We also examined three major sources of power dissipation: dynamic, short circuit and leakage power, and introduced the basic concepts of power estimation. In next lecture, we will begin the first major topic, sources of power dissipation in CMOS circuit, where we will study each power component in greater detail. Thank you.